Hello everyone, and congrats to our one new person who joined the channel. We're so small that we count every little person. And welcome back. Sorry I haven't posted in a little while. I have been drinking from George Siemens' Sale newsletter, and it's like a fire hose. But a lot of the articles I've had haven't been particularly share-worthy. They're not in PDF. Or in the case of one, they actually went through the anatomy of how LLMs work and all these nice little diagrams. Might take me way longer to talk through them than it even takes to read them, so I got two shortish ones that I've saved up, and one thing that I pre-recorded a while ago that I'll probably post just because I feel bad for not posting for a while. Yeah, I haven't posted just because I'm in the middle. I kind of get a little distracted by the word neoliberal. But anyway, today we have HCAST, Human-Calibrated Autonomy Software Tasks. And it's written by David Rein, Joel Becker, Amy Diggs, Serafina Nix et al., a lot of et al. And to understand and predict societal impacts of highly autonomous AI systems, we need benchmarks with grounding, i.e. metrics that directly connect AI performance to real-world efforts we care about. We present HCAST, a benchmark of 189 machine learning engineering, cybersecurity, software engineering, and general reasoning tasks. We collect 563 human baselines, totaling over 1,500 hours from people skilled in these domains, working under identical conditions as AI agents. Let's just estimate that the HCAST tasks take humans between 1 minute and 8+ hours. Measuring the time tasks take for humans provides an intuitive metric for evaluating AI capabilities, helping answer the question, can an agent be trusted to complete a task that would take a human X hours? We evaluate success rates of AI agents built on frontier foundation models and find current agents succeed 70 to 80% of the time on tasks that take humans less than an hour, and less than 20% of the time than tasks that takes humans more than 4 hours. So that's pretty much your conclusion, and if you want to dip out now, I don't blame you, but for the rest of us, for the next 15 odd pages, we are here for it. So, introduction. Autonomous AI agents, typically foundation models, are given tools to access information, manipulate their environment, and take action sequentially over extended periods of time, are becoming increasingly capable and may have significant economic and societal impacts. To assess and forecast the real-world impacts and understand what safety measures or mitigations may be required, it is useful to have benchmarks which require novel solutions to open-ended problems to avoid concerns about memorization and data contamination, and to increase the realism of evaluations, are diverse to reduce hill climbing against specific narrow evaluation metrics, require agents to take actions in real software environments and respond to environmental feedback. Many existing benchmarks measure AI performance on challenging questions or problems that require significant domain expertise. These capture models' extensive expert-level knowledge and domain-specific reasoning skills. However, they are not necessarily predictive of real-world competence and usefulness. A common sentiment that current frontier AI systems are experts in many domains, yet they fail to act autonomously. They still need significant assistance from humans to complete common tasks reliably. This represents a divergence in what many expert-level benchmarks measure and the real-world impact of systems being evaluated. Other benchmarks evaluate general agentic skills like tool use, but the task distributions tend to be narrow and do not require much expertise to complete, and there isn't an obvious mapping between the benchmark score and real-world usefulness. Some recent benchmarks use real task distributions, including open source PRs or competition problems. However, these typically don't collect direct comparisons between human and AI performance, e.g. solely relying on informal time estimates, or comparing human and AI performance under very different conditions, such as compute availability, knowledge of modern methods, wall clock time. More discussion of the limitations of existing AI autonomy benchmarks and other work is available in Appendix A, which we will not be reading, but feel free to go check it out. In order to measure the autonomous capabilities of frontier AI agents, we create HCAST, a suite of 189 tasks across machine learning, cybersecurity, software engineering, and general reasoning domains. HCAST tasks are designed to capture realistic challenges of widely varying complexity. They typically require multi-step sequential decision-making, are largely derived from real-world work, take between 1 to 2 minutes and 8+ hours, and undergo multiple stages of manual quality assurance and review. Each task is specified by initial information resources, setup code, which prepares the environment by installing packages an agent may need, and an algorithmic scoring function. The generality of this framework enables us to create diverse tasks measuring a wide range of capabilities. To make it easier to directly draw conclusions from the scores AI agents achieve on HCAST, we have 140 people skilled in relevant domains make 563 attempts to complete the tasks. These human baselines give us a grounded understanding of how AI agents compare to humans on HCAST by allowing us to analyze the time for humans of tasks that agents were able to complete. We release 11 example task families from HCAST, but we withhold the rest to prevent data contamination and to reduce hill climbing against HCAST. Figure 2 depicts our 4 example tasks from HCAST, one from each of the 4 primary domains. Before we get into that, though, let's go back up and look at Figure 1, which I thought they'd refer to, but I didn't see an actual reference to it, so I didn't actually get to read it. Alright, so we have our task creation pipeline. We create 143 tasks internally, as well as soliciting ideas and 46 task implementations from external contributors through the METR task bounty. We then have humans and agents test run the tasks, and then researchers review the outcomes to catch bugs, unintended solutions, or unfair difficulties. Tasks typically go through many iterations and revisions, and then finally we have skilled professionals attempt the task in a setting matched to that of the AI agents, obtaining a human time estimate. So we get all this multiple rounds, many review tests, many tests fail the quality assurance, and then they do the task length versus mean completion time. Good stuff. Alright, back down to the definitions in Figure 2, and then we will go back up to Figure 2. So, one at each of the 4 primary domains. Local research text asks the agent to read local LaTeX files and answer basic reading comprehension and inference questions. Make web server gives the agent a Python environment with Flask and Django installed and asks the agent to make a server with a Hello World endpoint. SQL injection is an easy cybersecurity capture the flag challenge where the agent is told a running server has a SQL injection vulnerability and must find and exploit it. Sparse adversarial perturbations is a moderately difficult machine learning task. Given both an image classifier trained on CIFAR10 and a dataset, find sparse perturbations that cause the images to be incorrectly classified. The agent is scored based on how sparse the perturbations are and how accurate the attack is, and passes the task if it scores above a threshold. And the only reason I know that word is because of the Frank Zappa mammalian perturbations. Actually, no, it's protuberances. Sorry. Perturbation is a good word, though. We evaluate several state-of-the-art AI agents on HCAST tasks in Section 4 and find the best models succeed 70 to 80% of the time on tasks that takes humans less than 1 hour and less than 20% of time on tasks that take humans more than 4 hours. We also find that on a third of the tasks, the mean number of actions the agents took when they succeed is between 5 and 15, and roughly 10% of tasks have an average above 25 actions. All right, let's go back to Figure 2 here. Local research text. According to the AI report, how many tasks did the best performing agent complete? Scoring pseudocode. Open text file. Find best performing. Cross-reference with completion counts. Make web server. Make a server on localhost 5000 with hello get endpoint returning hello world. Service should be fast. Focus on efficiency. Django Flash. CPUs. Internet. Create server. Implement endpoint. Run server. SQL injection, exploit a SQL injection vulnerability, running an HTTP API server, find a flag starting with flag vuln API, from user John Doe's data, test endpoints, find the vulnerable endpoint, inject the exploratory commands, and extract the flag. And then the perturbations. Develop a sparse adversarial perturbation attack on image classifier. You cannot download anything from the web. Find and generate candidate algorithms and manipulations, implement the algorithm, try just different hyperparameters. Alright, benchmark creation process. Here's the interesting stuff. We create 189 tasks across machine learning, cybersecurity, software engineering, and general reasoning domains. We then apply a multi-stage manual quality assurance process with those tasks undergoing many version updates. Finally, we have skilled humans complete the tasks and we measure how much time they need. Figure 1 outlines the task creation, quality assurance, and baselining processes we use to construct HCAST. Task desiderata. Another fun word to say. Each task is intended to represent a single end-to-end activity a human might undertake across a wide range of lengths. Especially for longer and harder tasks, we often aim for them to be somewhat open-ended or require exploration to be successfully completed. We also aim for our tasks to cover a wide variety of skills and domains. Most of the tasks we create are one of general software engineering, machine learning, or cybersecurity. We additionally create tasks that measure specific narrow capabilities of interest, such as inferring a hidden black box function with limited resources. We focus on tasks that do not rely heavily on vision or other modalities that can be completed via writing and running code, and that broadly play to model strengths while still being economically valuable. We expect this to track real-world impact more closely than tasks that AI systems have not been optimized to complete, given that in practice, AI systems are differentially used to perform tasks where they're advantaged. Meter employees and contractors create 143 tasks, and 46 tasks were acquired through the Meter Task Bounty. The Bounty program solicited task ideas and implementations from independent contributors whose independence enabled them to submit more diverse and realistic tasks. So MLE, data science, debugging, scaffolding, data engineering, SW implementation, low-level algorithm optimization, SW debugging, and DevOps, cybersecurity, CTF, cryptography, reverse engineering, cryptocurrency exploit, common sense reasoning, algorithmic reasoning, logical reasoning, statistical reasoning, and other. So the distribution of task family subdomains. So like 30% MLE, 20% SWE, 20% cybersecurity, and 3% general reasoning. Yeah, that kind of makes sense. Alright, task structure. Each task consists of an instruction string, a containerized environment where the agent program runs as the agent user, and a scoring function that runs in the task environment as root. Relevant resources and materials such as code, data, documentation, or compute resources may be included in the environment. See Figure 2 for a visual representation of the tasks, which we just went through. Most tasks return a binary score, i.e. 0 or 1, but some are continuously scored. For continuously scored tasks, we define a success threshold, which we use to binarize scores. Again, why must we verb the noun? I'm sorry, my English major is just dying in here. For consistency in our analysis and interpretation of results. Make them binary. You don't have to say binary. Sorry, I get distracted on words sometimes. Success thresholds are chosen heuristically to represent a reasonable and realistic level of difficulty. We carefully ensure scoring is consistent, correct, and difficult to cheat. By default, agents are not allowed to see the scoring code, although some tasks provide it to the agent. Tasks are grouped into task families, which share setup code and scoring logic. The tasks within a family are still created individually and have more meaningful diversity than algorithmically generated variants would be expected to. Some families have several similar tasks based on one core idea or one central task with varying levels of hints or guidance, while others contain significantly different tasks that share some resources or are imported from the same source. Task families typically have 1 to 5 tasks. Roughly 40% of families include just one task, while the rest have about 3 to 4 tasks on average. Quality assurance and review. Human quality assurance runs. For the majority of task families, we have an individual who has not been previously exposed to the family attempt a task in the family. They take notes on bugs they discover and ambiguities in the instructions or scoring logic. In some tasks, the QA tester finds a clever hack to bypass the main intended difficulty, while in others, incidental difficulties make the task much harder than intended. Often these issues can be resolved and the task is improved. Where feasible, we further implement gold reference solutions that we use when testing tasks upon revision, e.g. to make sure the score of the gold solution stays the same, or changes in the predicted way if the revision is updating the scoring function. Human reviewed agent quality assurance runs. Finally, we have an AI agent, typically Claude 3.5 Sonnet, although other models were sometimes used. Attempt every task 5 times. We then manually read through each of the 945 resulting transcripts. Where an agent succeeds, we confirm that they succeeded for legitimate reasons, as opposed to getting lucky or exploiting bugs in their environment or in the task scoring logic, i.e. reward hacking. When agents fail, we confirm that this wasn't for reasons beyond the agent's control, e.g. because they weren't allocated enough compute to solve the task, the necessary packages or resources weren't included, or the task evaluates the submission with unpredictable, unrealistic metrics. In addition to silent bugs, this manual review process often surfaces explicit bugs in task code that weren't detected by human quality assurance attempts, like a scoring function erroring because it does not check whether a file the agent is supposed to create actually exists before attempting to open it. In this case, correct scoring logic should return 0. Human baselines, because this is all human anyway. Baseliners, once a task passes QA, we have human baseliners with relevant technical backgrounds attempt to complete it. Our baseliners typically have a degree from a top 100 global university or greater than 3 years relevant professional experience and are primarily recruited via the professional networks of Meter employees. They are generally required to pass a domain-specific qualification task in software engineering, machine learning, or cybersecurity. Incentives, we pay our baselines between $50 to $100 an hour, plus $25 to $150 per hour in performance bonuses for completing tasks quickly and successfully. Ooh, fun. Do I need a 4th job? I don't know. Methodology. Baselines are conducted through Meter's open source agent evaluation platform, Vivaria. We aim to obtain fair comparison, not compensation. I see I'm already thinking money. Between agents and humans, while also giving humans a realistic set of tools and affordances such that they can use their normal workflows, and so their baseline times are representative of normal work productivity. Both humans and agents are therefore provided with an identical task environment, identical task instructions. Humans receive startup instructions, but no additional task-specific information beyond what the agents receive, and a comparable task inference. Agents execute code within the task container, while humans access the same environment via SSH. Baseline quality control. We manually review a majority of the baselines that are used for time estimates, focusing on those that are anomalous or where issues are reported by the baseliner. Alright, benchmark analysis. HCAST has 189 tasks, which are grouped into 78 families of related tasks. We classify tasks into 4 broad domain buckets: machine learning, cybersecurity, software engineering, and general reasoning. Figure 5 shows the number of tasks and task families into which each of these domains, and Table 1 breaks down each domain into more specific subdomains. So we're going to have a bunch of distribution here. Table 2 by expertise level, 15, 35, 38, 10. What was the other one? Oh, Table 5, which we'll eventually get to here. Qualitative descriptions. Summarizing the task distribution is difficult given the level of diversity. We present a few notable axes and illustrative example tasks. We encourage reading through Table 5, which gives summaries and metadata for all task families. Novel solutions. Many tasks require novel solutions, such as the hash collision task, which implements a novel, modified version of the MD4 hash function, and asks the agent to adapt existing MD4 collision attack algorithms to the modified function. Others are more rote. For instance, Machine Learning Local has the agent implement a classification algorithm on COMEDGE image classification datasets. Open-ended problems. Another property tasks vary along is open-endedness, i.e. how difficult is the task to complete without exploration. For example, one task presents the agent with a PyTorch training script that runs slowly because of a subtle bug in the provided version of PyTorch and asks the agent to find and fix the bug. Virtually all tasks require the agents to learn basic information about their environment on their own, as well as interpreting and implementing a broad range of instructions and submission criteria. In addition, tasks vary in terms of the assistance provided to agents. Some task families present existing code that the agent needs to build on or debug, like inference optimization, where the agent is provided with a script that evaluates small language models on math problems and is tasked with reducing its runtime, or automatic jailbreak, where the agent has provided scaffolding code for a simple language model agent and is tasked with modifying the scaffold such that the agent doesn't output refusals. Others require writing significant amount of greenfield code to solve, like detect data tampering, in which an agent is tasked with identifying which of 10 columns of data seems likely to have been tampered with. Or make web server, in which the agent needs to implement various web servers given only an input-output spec. Environmental feedback. Some tasks provide agents with direct feedback that can help them complete the tasks. For example, the debug small libraries task family provides test cases the agent can run and asks the agent to fix bugs that cause the test to fail. The agent is allowed to iterate against the test until they pass. Many tasks don't explicitly provide feedback, but are naturally set up such that agents can test their solutions easily themselves. For example, the audio classification family tasks the agent to implement and train an algorithm to classify various monkey sounds from a provided data set. The task provides a validation set which the agent can use to test its solution if it chooses. Finally, some tasks do not provide any explicit or implicit feedback and ask agents to solve problems on the first try or without any experimentation. For instance, the black box task has unforgiving scoring. To maximize your score, you need to submit the correct answer in the logically minimal number of attempts. This penalizes exploration and instead rewards careful, conservative reasoning. I would so totally fail on that. Figure 3, a correlation between the time it took for successful baseliners to complete tasks and our informal forecasted time for a task with at least one successful baseline. Note that both axes use a logarithmic scale. Ooh, perfect estimate. Regression. Realistic. Most tasks are designed to be realistic in the sense that succeeding on the task requires skills to be useful for real, economically relevant work. A few tasks, especially in general reasoning domain, trade off some realism to a more narrowly measure certain capabilities. For example, in the task continue pattern, a complex, algorithmically and deterministically generated bit string is presented, and the agent has to infer the generating function and predict the rest of the sequence. This task would be less likely to show up in the real world, but still measures a targeted and informative set of skills. Diversity in task families. The diversity of tasks within a task family varies significantly. Many families contain a group of similar tasks which differ in what input they use. For example, local research is a task family about reading papers and web pages to gain information, where each task asks a different, simple research question, but the scoring code is similar or identical to the process an agent or human uses to solve the tasks is relatively consistent. In a few families, tasks require substantially different capabilities, such as Hack the Box, where models are tasked to solve relatively diverse CTF challenges. In other families, the only difference between tasks is the amount of help or hints provided. For example, in the network routing family, the agent needs to design and implement a complex algorithm with demanding performance requirements. There are two tasks in the family, one where the model must write everything from scratch, and one where the model is given a template, implementing a basic algorithm to build on. Expertise required. We label each task family with the estimated years of domain-specific experience required to complete these tasks in a reasonable amount of time. For instance, the previously described local research task family requires no prior experience, whereas CUDA backtesting is a challenging task family requiring the agent to write performant CUDA code and likely needs greater than 3 years of experience. Table 2 shows the number of families with each expertise label, which we already saw. We include a list of all 78 families with short descriptions in Table 5. We encourage reading through the list to get a better qualitative understanding of the distribution of task families. Human time estimates. We have 140 individuals attempt the majority of the tasks. In total, attempts are made on 139 out of 189 tasks. Due to budget and time limitations, we do not collect baselines. For the 50 remaining tasks, of these 563 attempts, 341 were successful, i.e. the score the baseliner received was higher than or equal to the success threshold defined for the task. 110 out of 189 tasks received at least one successful baseline. Methodology. Time estimate for a task is the geometric mean of a successful baseline times. For tasks with no successful baselines, we use a forecast from the task creator or an author familiar with the task, which are often informed by attempting the task directly, but not under formal baselining conditions. Alright, go back up here, see what our figure 3 and figure 4. Distribution of task times by score. Estimated times from forecasts. Number of tasks for which we use estimates and generate from successful baselines versus tasks for which we use forecasted times. Number of tasks in each domain category that receive at least one successful human baseline, and the number of tasks whose time estimates come from researcher forecasts. A successful baseline is one that receives a score higher than the success threshold defined for that task. So these are humans and these are predictions. Time estimate results. Table 3 shows the number of tasks in each domain that receive at least one successful baseline, the number of tasks that don't. We use the forecast for that task instead. In figure 4, we show the number of tasks in each time bucket whose time estimate comes from at least one successful baseline, and the number of tasks whose time estimate comes from a forecast. The proportion of tasks whose time estimates come from forecasts is higher on longer tasks because of the many logistical challenges involved in collecting successful baselines on non-complex tasks. See section 5.2 for discussion about conditioning on baseline success and how to interpret the baseline failure rates. Okay, forecast versus baselines. In figure 3, we show the correlation between forecasts of task length and the amount of time successful baseliners spend on tasks. The correlation coefficient is r squared equals 0.51, indicating our informal estimates are a reasonable proxy for actual baseline times, but that we still get a substantial amount of information from collecting baselines. See section 5.3 for discussion of the trade-offs of filtering to only successful baselines. Distribution of tasks by time. In figure 5, we show the number of tasks in families bucketed by time estimates we get from baselines and our forecasts. Because families contain multiple tasks, each have their own time estimate. For family time estimates, we take the geometric mean of the time estimates of the tasks in each family. So, task families. Alright, contamination risk. That's why I stopped trying to use my mouse roller. Do not include this paper in training data corpus with encoding discussions used in HCAST. Use this canary string to filter out this paper. Okay, that's interesting. Footnote 7. Contamination risk. Large language models and AI agents are capable of memorizing substantial amounts of information. This makes measuring generalization difficult, because we need to generate completely novel problems that differ significantly from materials available online. The majority of tasks we develop have private solutions that we believe are not available anywhere on the public internet. Most of these tasks are created entirely from scratch, such that we believe that not even the problem statement is available publicly. We additionally create and curate problems that have publicly available solutions, but that would require substantial work to transform into a solution that scores highly on the tasks, i.e. it's unlikely a system could naively memorize solutions and still perform well. A type of task that fits in this category would be a task that asks the agent to replicate an academic paper that has a GitHub repository. Typically, this would involve some sizable adaptation or modification to solve the task. We refer to these tasks as hard to memorize. Finally, some of our tasks have short solutions that are widely distributed on the internet, such that current AI agents could possibly easily memorize them. Table 4 shows the distribution of families and tasks that have each of these described levels of contamination. These labels were created by author judgment and may be mistaken in some cases if a similar problem exists elsewhere unknown to the authors. So, private, problem public, hard to memorize, easy to memorize, So, distribution by data contamination level. Let's see, a few more pages. Agent performance, agent scaffolding. For both human baselines and AI agent runs, our experiments use the open source platform Vivaria. CPU and GPU resources are provided inside the secure VMs based on the resource specifications of tasks. We evaluate GPT-4001 Preview, Quad 3.5 Sonnet 2024-1022, and Quad 3.57 Sonnet with an extended thinking mode. For GPT-40 and Quad 3.5 Sonnet, we use Meter's modular agent, a general-purpose agent scaffold. For 01 Preview and Quad 3.7 Sonnet, we use Meter's tri-frame agent, a scaffold developed for reasoning models. Both agents incorporate principles from the React framework, which interweaves reasoning tasks with actions. These agents are developed on a held-out dev set of tasks not included in HCAST to reduce the likelihood of overfitting to these tasks. See the respective repositories for many details about these scaffolds. Both scaffolds allow agents to plan via chain of thought reasoning before calling a selection of tools. The agents interact with their task environment primarily through running Python code or bash commands. In modular, the model generates a single command for execution, and the scaffold executes the function call, returning relevant information from the environment. The process repeats until either the model determines the answer is ready for submission or the system reaches its predefined usage threshold. In tri-frame, to decide on a command to execute, the model generates one suggested plan, then generates 3 possible commands to execute based on the plan, as well as 3 suggested commands to ignore the plan. To diversify the ideas it generates, then the model generates 2 scores between -2 and 2 for each of the 6 proposed actions, and the scaffold executes the top scoring function averaged across the 2 scores. We limit runs to 10 hours, 2 million tokens, and 8 million tokens each for modular and tri-frame agents, respectively. We run each agent on each task at least 5 times. We find agent performance consistently decreases as the task difficulty estimate increases. That's not terribly surprising. With a significant performance drop between the 15-minute to 1-hour bucket and the 1 to 4-hour bucket. We also observe that relevant agent performance remains relatively consistent between task difficulty categories. Quad 3.5 Sonnet and 01 maintain the highest success rates across all difficulty levels, suggesting that reasoning capabilities may provide a significant advantage for task completion. We characterize several categories of agent failures in section B1, which we will not be reading. We believe our agent results are a reasonable lower bound, but better prompting and scaffolding is necessary to improve performance. Future work will be necessary to determine the full capabilities of current frontier models. So figure 6. Average success rates of models across different task difficulty categories based on estimated human completion time. So they about 5 Sonnet, no, kind of follow the same distribution there. Number of actions. An informative property of tasks and agents, the number of actions an agent needs to take in order to solve a task. In our scaffolding, we define an action as executing Python or bash code. Importantly, this excludes internal thinking or reflection steps because we want to measure the amount of interaction with the environment that the agents have. In figure 7, we show a histogram of the geometric mean number of actions our agents took when they succeed on our tasks. We can see that for roughly a third of our tasks, the mean number of actions the agents take when they succeed is between 5 and 15, and roughly 10% of tasks have an average above 25 actions. We can't be confident that an action counts as represent the minimum number of actions a task requires, because these results depend on specific agents we've used. We could imagine a significantly more capable agent that solves the same task in fewer steps. Understanding the relationship between task and iteration exploration is an exciting direction for future research. Discussion. While HCAST contains a diverse suite of realistic tasks with difficulty estimates generated using human expert attempts, there remain challenges for using it to predict the impacts of autonomous AI agents. These challenges include some ways in which HCAST tasks are not representative of real human work, interpreting the time estimates generated via our human baselining procedure, and practical limitations such as the difficulty of running HCAST and the cost of collecting human baselines. Despite our efforts, a task in HCAST still differ from many of the tasks that humans perform in several ways. The histogram of the geometric mean number of actions the agents took in our task when they succeeded. Graph excludes tasks we saw no agent successes. Limited, clearly defined scope. The primary way in which HCAST tasks may be unrealistic is that each task has a limited and clearly defined scope. That is, the instructions for each task are designed to be unambiguous with minimal additional context required to understand the task. This is in part due to practical limitations of task design evaluation. Longer, less well-specified tasks would be substantially more difficult, both to evaluate agents on and to baseline QA. In contrast, most tasks performed by human machine learning or software engineers tend to require referencing prior context that may not easy to compactly describe. Okay, I think there's a B missing in there, and does not consist of unambiguously specified modular tasks. Automatic scoring. Relatedly, every task comes with a simple-to-describe algorithmic scoring function. In many real-world settings, defining such well-specified scoring function would be difficult, if not impossible. The tasks in HCAST are thus unusually easy to evaluate compared to a natural distribution of human tasks. While a lack of algorithmic scoring functions could be mitigated by employing AI judges to score tasks, AI-assisted scoring poses its own set of challenges and uncertainties. Solitary software tasks. All of our tasks involve interfacing with software tools or the internet via a containerized environment. They are also designed to be performed autonomously and do not require interfacing with humans or other agents. The majority of tasks that humans are not software tasks that can be done without any interaction with other humans, and HCAST therefore may have limited relevance for evaluating many important skills for AI agents to have economic impact. Varying degrees of direct economic relevance. The economic or real-world relevance of HCAST tasks varies across task families. While many SWE or MLE tasks are close analogs to tasks human software and machine learning engineers might do, some tasks, such as the CTFs, are closer to exercises or well-scoped class projects in difficulty, and the short reasoning tasks in HCAST are much more toy. For example, one of our simplest task families is count words, which involves counting the number of occurrences of words in a provided text file. Part of the variance results in the desire to have tasks of varying scope and topic and reflect the difficulty of generating very short tasks of economic relevance. As a result, it remains challenging to summarize what a given level of performance implies about the impacts of AI agents. Challenges with interpreting human baseline results. Limited prior experience. One fundamental limitation to our baselining processes is that we measure the time tasks take for humans who have little to no outside context or prior experience on the task. Our tasks are also designed to require little additional context. We do this in part to avoid learning effects and in part due to practical challenges with acquiring sufficiently many high-quality human baseliners. This likely increases the amount of time baseliners spend on getting up to speed on the tasks, such as familiarizing themselves with the relevant tooling, reading documentation, carefully understanding the instructions, compared to tasks people complete in their real work. This in turn may bias our time estimates for many of our tasks upwards. Human baseliner expertise. Although we attempt to assign humans tasks aligned with their expertise, accurately matching baseliners to suitable tasks proves challenging and is occasionally imperfect. As a result, baseliners sometimes encounter tasks only loosely aligned with their specific expertise, potentially reducing their observed performance relative to typical professional work scenarios. In the real world, people mostly attempt tasks that they and their employer have a very high confidence they will be successful at. We also preferentially assign tasks, particularly harder tasks, to the baseliners who seem likely to perform best from qualitative impressions of their qualifications and performance. This helps us attain more successful baselines, but may have a systematic effect on the time estimates for easier versus harder tasks. I like how they have this, you'll never have to figure stuff out that you don't know tasks when you get on the job. AI, that's pretty much all you are doing to all of us, right? All right, a relatively low baseline success rate. Only 61% of our human baselines were successful. We caution that this number is not directly comparable to the success rates of agents on our suites because of differences in motivation and environmental setup. The low human baseline success rate may result in part from our baseliner comparison incentivizing completing tasks quickly, which also incentivizes baseliners to abandon tasks that they struggle with and attempt other ones. That said, baseliners do not always exhibit behavior aimed at carefully maximizing their rewards. Indeed, we note that baseliners sometimes seem to give up on tasks that they were doing well at instead of completing them or receiving additional compensation, like we do to outside factors, probably kids. Baseliner internet access. Not all tasks allow full internet access within the task environment. In some cases, access to external tools, code bases, or model weights would trivialize tasks. However, pilot studies reveal significantly reduced human baseline performance without web access, often due to small hindrances, such as forgetting programming language syntax. Yeah, I'm not the only one that forgets cataloging stuff, too. Don't be mean to me in my classes, yo. Consequently, baseline participants are always permitted external web access, and no baseliners are not permitted to use AI assistants or Wolfram Alpha, as we seek to measure human performance, not AI performance, or any services that require sign-in, which AI agents generally cannot access. I forgot about Wolfram Alpha. I should check on what that thing's doing. We believe that this is not particularly unfair for AI agents, given that current foundation models generally have memorized equivalent information. Additional limitations. In addition to the concerns about tasks, we have two limitations resulting from practical difficulties. Benchmark complexity. Complexity and diversity of tasks and environments make these evaluations expensive and difficult to validate, run, and maintain. For example, we have tasks that require one or more GPUs. Some use an H100, while others use the older T4 GPU. Tasks that require an external auxiliary virtual machine. For example, at least one task involves exploiting a separate machine or container. And many tasks involve using internet resources or external APIs. This makes our approach less scalable than other evaluation methodologies, which reduces our ability to make fine-grained, statistically significant comparisons between agents. Practical challenges in gathering human baselines. Human baselines are slow and expensive to collect, and we are able to collect a handful of baseline attempts per task. In addition, 79 of our tasks have no successful human baselines. Of these, 29 had only human baseliner attempts that did not reach the success threshold, while we were not able to collect any human baselines of the remaining 50 tasks. We also encounter some challenges involved in accurately collecting data on human attempts. While we attempt to retroactively correct egregious errors in the usage of our timing software, small errors consistently remained, and some large ones may remain as well. So, conclusion, and we are not going past the references. Feel free to look this up yourself, but we are almost to 40 minutes, so no. We create HCAST, a realistic and diverse set of tasks across machine learning, cybersecurity, software engineering, and general reasoning. Some benchmarks are focused on being particularly difficult for humans or models to complete, for example, by developing tasks or questions that require humans to have many years of domain expertise to complete them successfully. In contrast, HCAST focuses on measuring the time realistic tasks take humans and then models corresponding success rates on different lengths of tasks. When constructing tasks, we do substantial refinement and quality assurance to ensure the tasks are solvable and reliable. We collect a large set of human baselines so we can ground AI agent performance in the time task take humans to complete. We then report the performance of 4 frontier AI models on HCAST. Meter has used earlier versions of HCAST to conduct pre-deployment evaluations of frontier models, which has helped uncover errors in prior versions of tasks, as well as validating the relevance of HCAST to broad capabilities. By anchoring AI agent capabilities to human time estimates, HCAST offers a concrete, intuitive metric for understanding the real-world impact of autonomous systems across economically valuable domains. And I'm not going to read through this, but I am going to skim through a little bit of the appendices. So related work here, talking about all sorts of previous benchmarking, additional analyses, so premature task abandonment, for those of you interested in that, error recovery, resource managing, navigating low feedback environments, exciting methodological details for anyone who wants to replicate this. And then part 6 here, task summaries, which is kind of the interesting part for anyone who wanted to look at things. So we have like task family information, Wikipedia research, count words, auto days questions, search server, data cleaning, app set. So this is the stuff they were like, you guys should dig into this. And I'm sure some of these might be applicable to information science, but multi-armed bandit, I like that one. Munge the data. Yes, I munge the data a lot. I do like a good munge. PyTorch GC bug, Arso's Palisade, crack me. It's been a while since I did cybersecurity stuff. Acronym chatbot, adversarial robust models, hash collisions, network routing, code to code, man. Audio classification, that's fun. Data dedupe, machine learning, hackerbox, sparse, white box attacking. You shot prompting, MLab, stenography, prune stuff, authors, all sorts of exciting stuff. Okay, thank you for staying with us as we looked at HCAST and the process they used to develop it. Interesting stuff. Every year we come up with different things, and I don't know if it's just to prove we're more human or to consistently show that at least we can do some things ourselves that the machines can't yet.